All right, so this is going to be just a quick little video on how to determine if a relationship is a function. So we've got 3 standards for the test again. This first standard is going to be just seeing, can you look at a thing, a relationship, and decide, is it a function, a functional machine, or is it not? We'll talk about the domain and the range tomorrow, but for today, we're just going to think like, how can we take a look at a machine and think if it's functioning properly? If it's functioning properly, we call that special machine a function, right? And so a relation is just a machine that's got a relationship between inputs and outputs. And if that relationship is special, a functional one, we call it a function. Where every input, where every element of the input, that's known as the domain. So we're not going to use the phrase input or output anymore. We're going to be using domain, is paired with exactly one element of the output known as the range. So before on Desmos, you had a machine that put, let's say hello in. So hello went in, P came out. Hello was known as the domain, and P is now known as the range. So your outputs should be known as range. Your domain is known as inputs. So if the relationship is predictable and it's functioning well, then every input will have one singular output, meaning that every time you put that thing in the machine over and over and over, you can get a predictable response. So if I look at several of these modalities, so now the machines can be given to you this way, this way, this way, or this way. And the upside of these things is if you don't like the way that one thing is written, you can switch it into any representation that you like. Some kids love mappings and hate charts. Some kids love tables but not ordered pairs, and vice versa, and all that kind of stuff, all right? So the upside is that you can convert any representation, any modality from one to the other. All right, so let's look at this one. Ordered pairs. In an ordered pair, that's the input, that's the output. Makes sense, right? Like 4 goes into the machine, 3 and 1 comes out. 3 goes in, 5 goes out, 8 goes in, 7 goes out, 6 and 2. So far, that to me looks like I have no evidence that the machine is broken. Everything is predictable. Right now, all I know is that 4 goes in, 1 goes out. I don't have any evidence that if you put 4 in again, it's going to give you something different. So right now, I'm going to say this is a function just based on the ordered pairs, okay? Now, let's just say I was confused and I was like, I'm not really sure if it's a function or not, but I like tables. So a table, I can just take all the x's. So the first x I see is I have a 4. 4 gives me 1. 3 gives me 5. 8 gives me 7. 6 gives me 2. So I can rewrite from a set of ordered pairs into a table. And by the way, I can go backwards too. If I really wanted to, I could just take this and make it look like 4, 1. 3 is first, then 5, 8, then 7, 6, then 2. And now notice all those ordered pairs look just like the ones here above, right? So switching around can be a really powerful tool. Every modality has pros and cons. The upside about a table is that it looks really clean. You can see a lot of things in there, but the table could be really, really long and really overwhelming. So sometimes if there's a lot of data, looking at a table might not be really efficient. All right, this little part is just going to be about switching from different modalities. So I'm just going to go to this one here diagonally now. Again, X is always going to be your inputs. The first thing is always your input. The second thing is always your output, again, known as range. So what domains do I see? I'm going to organize them, by the way, numerically. So I'm looking at the chart here, and the first thing the lowest number I see is a 3, then a 4, then a 6, then an 8. I'm also going to reorganize the Y's, the outputs, numerically. So in order, smallest is 1, then there's a 2, then a 5, and the 7. And the reason I can rearrange them is because the way that we show connections is not across, it's through arrows. So the input of 3 gave me a 5. So that means I'm going to connect 3 to a 5 with an arrow like this. 4 gives me 1, so I'm going to draw it like this. In the table, 8 gives me 7, so I'm going to draw the arrow from 8 to 7. And lastly, 6 gives me 2, and ta-da. So the difference between a table and a mapping is that in a table, you can organize them however you want, as long as 4 and 1 always pair together. Meaning, like, you can make this chart look like this. 3, 4, 6, 8. If you wanted to make it like that, you totally could, but 3 still has to be attached to 5. If you mess with the order on the left side, you can't leave this in this order, because now you're saying 3 gives you 1, and very clearly 3 is supposed to give you 5. So if you're going to mess with the order here, make sure that the right pairs are still attached. Okay? So that's how I would switch this to a mapping. Notice 3, the input is only attached to 1 output. 4 is only attached to 1 output. 6, the input only has 1 output. It's predictable. Everything I know, 6 is going to give me 2. I have no evidence that it won't. 4 is giving me 1 always. I have no evidence that there's something wrong with 4, or if there's something wrong with 3. Like, this all looks like it's functioning just fine. Okay, the graph. Again, now that we've got a lot of modalities, meaning a lot of boxes filled in, you can go in whatever order you want. I was given this, so I could have switched it to this first and then done this and this. So the order in which you switch these totally doesn't matter, whatever you like the best. But for me, to make a picture, I like using the ordered pairs. So I'm just going to copy them one more time here. 4, 1 is my first one, 3, 5, 8, 7, and then I think 6, 2. So I'm going to graph these. There are 8 numbers, but only 4 points. So 4, 1 is the location of 1 dot. Think about the first number and the second number as an address. If I tell you I live at 801, you don't know where I live. If I only gave you that my address begins with 801, what are you going to do, find all the 801s in the world? Same thing, if I only gave you that I live on Washington Street, what are you going to do? Going to go down Washington and knock on all the doors? It'd be really helpful if you had both of these pieces of information to be able to find exactly where I live. That's why we need both of those numbers. Just like part of an address, it's incomplete if you don't have both of these. So the 4, the number first, is always how you walk this way, your location sideways. And the second one is always your coordinate up. Just like case number and tiles, it's the same thing here. Over 4 across to case 4 to a height of 1. So even though this is not about tiles, you can always think about it like that. 3, again, you're always starting here at home base. 3, 5 is over to the right, 3 up to 1, 2, 3, 4, 5. 8, 7's off the grid. Here's 6, 7, there's 8. And then 7 up is here. So there's 8, 7. And then 6, 2. Over 6 to the side, 2 up. And I'll color code these just so you guys can see them. So 4, 1 was that pink one here. Then we had the green one, 6, 2. Then we had the purple one, which is this guy, and orange, which I'm just going to leave alone. Okay, so if somebody was going to ask you, is the relation a function? You've got 4 options to look at. You have to decide which one you like the best. Maybe you're going to love a picture. I really like mappings for this because you can tell really quickly that this input is only attached to 1 output. That 3 is giving me 5 every time. 4 is giving me 1. 6 is giving me 2. 8 is giving me 7. So I personally like to look at a mapping. That's what I would look at for me. It's yes, it's a function. I looked at the mapping. because you could see the arrows clearly. All right, let's do another example, and then you'll do one on your own. Okay, in this table, we are starting with a table, so now we can go to any direction that we want. I'm going to go with this direction. I don't know why I'm doing that, but that's fine. Mapping. No, you know what? Since we did that before, let's do the graph. So graphing, I'm going to convert these to ordered pairs. That's how I know their location. So now actually, these are the correct answers for this. So yay, saved ourselves a step. Just taking and copying, literally just putting parentheses around each of them. So don't overthink it, it's just left to right. Okay, so -3, 4, if I was gonna graph that. -3 to the left and 4 up. So that's the first dot. I can't stop just here because I need 2 locations. 2 to the right, 1 down. 1 to the side, none up. 1 to the side, none up is here. Left 3, down 4. So left 3, oops, 1, 2, 3, down 1, 2, 3, 4. So that's my last dot. So there are my 4 dots. And I'll do one more. Mapping. Always start with the smallest numbers, that's -3. I see -3 twice. I do not need to write it twice. In fact, you shouldn't. And I'll tell you why in a second. So I've got -3. Remember, we're going to draw arrows. So if I have an arrow out of this, I need to show an arrow from this too. And so I don't need to write it twice. Otherwise, every arrow would be the same. Then 1, then 2, 1, 2. All right, now we've got on the right side a -1 and a -4. I'm going to put the -4 first. -1, 0, 4. And now I'll draw my arrows. -3 goes to 4. 2 goes to -1. 1 goes to 0. -3 goes to -4. And there we go. Is this a function? Take a second. Doesn't matter which box you look in. Pick a box, narrow in and see, is it a function, yes or no? Nope, it's not. I'm going to look at the ordered pairs. Again, I really like a mapping, but I want to show you from here. I have a non-functioning machine. Here's the evidence of why it's not functioning. -3 is supposed to give me a 4. That's what it gave me. Next time around, -3 does not give me the same answer. These are not the same. So I can tell you right away it's not a function. And I like looking at the mapping. -3, this input gives me 2 different outputs. That's a problem. That machine is unpredictable. It is not functioning well. Hence, we would call it not a function. All right, so we can look at, again, doesn't matter where you look. You can look at the chart. You can see the same input giving you 2 different outputs. You can look at the ordered pairs, same input giving you 2 different outputs. You can look at the mapping and see the same input giving you 2 different outputs. The best question is, how do you look at a graph? Really quickly tell that this is not a function. So this is an example where it's not a function. Look at the graph up here. This is a function. So the next step will be, how do you look at this graph really quickly and figure out that there's a problem here, but not above? And we'll talk about that a little bit more tomorrow and a little bit more about the domain range. And that's it for Essentially Standard 1.1. Okay, hope this video helps finish up the quick little practice I have for you, and that's it. See you tomorrow.